About my research today, which is based on resorbable and deployable medical devices. So, if you look at the current clinical standards, there are resorbable medical devices, for example, PLLA based bone fixation device, and then PLLA reinforced with hydroxyapatite ceramic, which again is resorbable, which means that these can completely degrade inside the body without requiring any revision surgeries. On the other hand, we have deployable medical devices like nitinol based stents, which can be implanted inside the body in a minimally invasive manner, thereby being more patient compliant and reducing costs and pain to the patient. However, there are very few examples which combine both these resorbability and deployability feature inside a medical device, barring a few exceptions. PLLA based absorbable and balloon deployable stents. But then these have inherent disadvantages, like balloon deployability is not accessible to most parts of the body. Therefore, we need innovation and in materials as well as manufacturing technologies to have both these features in a medical device. For that purpose, we utilize 4D printing of ceramic particles reinforced polymer composites for deployable medical devices. We take this PLA based shape memory polymer, which is also biocompatible and bioresorbable. And then we have iron oxide nanoparticles, which can respond to inductive heating, and then they are also biocompatible. So this is the overall scheme of the work, which basically includes 3D printing of both PLMC neat polymer and then iron oxide ceramic infused polymer 3D printing into deployable scaffolds, and then we also show a dual actuation system by combining both polymer and composites in a single structure, and then we also show biocompatibility of these composites. So first case study is this printed composite can exhibit excellent shape recovery in the presence of alternating magnetic field. So this is the original structure 3D printed, and then this can be deformed and fixed into this temporary shape, which then placed inside alternating magnetic field. As you can see, over time, it can completely recover back into its original shape. And this happens at very physiologically relevant temperatures around 37 to 40 degrees Celsius. And the recovery time is around 15 seconds, which is very fast. And the extent of recovery is around 99%. Then we extended this proof of concept into showing that it can be extended into deployable and magnetically guided scaffolds. For example, here you have a tissue defect, which is very small. So we compress the original shape of the deployable scaffold into a form that can be easily implanted in a minimally invasive manner and can be deployed here. Once the scaffold is deployed like this, you can trigger the alternating magnetic field, which will then recover back to the original structure and then automatically fill the defect into the original size. So as you can see, over time this can recover back to the original porous structure. This can happen again in a matter of few seconds. Now, in addition to shape recovery, we can also guide these scaffolds by the help of permanent bar magnets, because they are magnetically responsive. These can be guided to the site of deployment, and then as shown, this can be triggered by alternating magnetic field. Now, as a proof of concept, we also showed that this shape recovery can also happen in a restrictive environment. Now, this can find applications in other biomedical applications like stents, where you would need the deployed shape to be uh, you know coming back to the original shape in a restrictive glass tube or something. Now, after all this, we also show that the composite of PLMC and iron oxide bioceramic shows in vitro biocompatibility by using various assays like live dead, actin nuclear, and Alamar blue assay in the presence of NIH33 cells. And then we also showed in vivo biocompatibility in animal Vista rat animal model, where you can show that there is no inflammatory response to these composites as well. Now, as a future directions, I would like to say that we can also have bioactive ceramics like hydroxyapatite, which can be coated over the surface of these 3D printed scaffolds, and then this 4D effect can be brought, wherein you have the shape recovery due to iron oxide ceramics, and then hydroxyapatite can enhance the bioactivity by promoting osteogenesis and so on. Now, alternatively, we can also have growth factors loaded onto the surface of the scaffolds, which can be then sustained release because of temperature induced shape recovery. Thank you so much.